much, Professor Shao. So I think it's actually very nice and fitting. It's been great to hear all these talks, and following Professor Lee is fun because I spent about the last 15 years working in exactly what he was describing, these hardware startups in robotics. And yes, it's incredibly challenging, but it's a great area to be in, and so I highly recommend it. The thing I want to talk to you today, and I think it's kind of fun that I'll talk today about agriculture, given that they put me right before lunch. So for better or worse, the thing between you and lunch is me talking about food for the next 20 minutes. So I apologize if what I talk about just makes you more hungry, but I think that's one of the keys that I think is really interesting for me, is that agriculture impacts us every day. It's what we eat, it impacts the clothing that we wear. So it's a really critical area to be working in. Let's see, I need to get this to go. So the thing about agriculture is that there's incredible demands on agriculture for producing food, and in particular, there are estimates that have been put out recently that we're going to require more and more food as the population continues to expand. Estimates even up between 60 and 100% growth in the next 30, 35 years. So this is a really large scale production, increases in productivity that we have to hit. And farmers are doing that with the same time being highly constrained. So if you look at farming, the amount of land that we have to farm on is fairly fixed. It's not going to double in the next 20 or 30 years. There are labor shortages going on, so both because of aging populations of the labor workforce, not really attractive jobs for many people, and also immigration laws, particularly in the US and Europe, that are really affecting the labor supply. So you throw all that together, so farming is a pretty difficult endeavor. And then you add on things that are happening in agriculture, in particular herbicide-resistant weeds becoming more and more prevalent. And it's something I'll talk about a lot today. But they've used for a long time these selective herbicides, and they're becoming less and less effective, and so weeds are becoming a much bigger problem. And then you throw into that also regulations, so more and more regulations, not just on herbicides, but on water usage, on fertilizer usage, things that really impact the environment, and so become more of a challenge for farmers to produce at higher productivity levels, which is really what's required to feed our population as it grows. So kind of with technology and the pace of technology accelerating, there's been great leaps in technology for agriculture. If you look over the last century, starting probably a little over 100 years ago with the introduction of the combustion engine into farming, John Deere introducing it in tractors, that led to a huge expansion in our ability to grow large quantities of food in these greater scales that are necessary. And you see these trends over the years, things like the introduction with new chemicals, new fertilizers, the ability to generate mass quantities of fertilizer, herbicides, insecticides, fungicides. So there's kind of this chemical revolution that happened about 50 or 60 years ago. And then again recently, in about the last 20 years, we've started to see the introduction of genetically modified crops. So these GMOs that people are familiar with and love them or hate them, they allowed us to, again, expand productivity in agriculture by pairing the genetically modified traits with the herbicides. If people are probably familiar with Roundup as a really classical example, where you can spray Roundup across the whole field and pair these traits together. And the GMOs also provide things like productivity, yield increases, insect repellents, things like that. So there's a lot of advantages of working with those, but there's the disadvantages as well. And what it's led to is this type of agriculture that is kind of shown by this picture. It's very broad acre agriculture, especially in the US. Big machines, big equipment, big farms, and it's a bit of a one-size-fits-all kind of viewpoint of agriculture. We plant the same seeds across large fields. We treat these fields with big boom sprayers that spray the same amount of chemical across the whole field. And we're trying almost to have every plant look identical and treat them all the same. But the reality is the ground changes, the weather changes, bugs hit different parts of the field, so every plant is not the same. And so what we're looking to do is kind of transform the way we look at agriculture from this very one-size-fits-all strategy to more of a plant-by-plant strategy. And it's part of kind of this growing trend in agriculture, which is what I'm calling the digital age of agriculture, where we're moving from kind of what we've done in the past to broader use of data and robotics, in particular, and computer vision, to introduce new techniques and new technologies that will help us continue with these productivity gains that are necessary to feed the population. And I'll talk some more about what I mean by that. Some of the digital components that have already started and are integrated into agriculture have started with GPS, so being able to localize, use GPS to figure out where you are on the farm and drive straight lines, do repeatable operations. With GPS, they've also coupled in data that gets collected either from satellites or now drones is very popular. And that allows farmers to control through some variable rate applications how they're applying materials in the field or what seeds they're using. And that's just getting started, but there's some real interest there, I think, in new technologies that allow us to use GPS and automated steering with variable rate technologies, the ability to change how much you're applying where and when in the field. And what I'll kind of get to is this notion that we want to do that not just kind of in a broad acre way, but at a very localized level with the plants. And we've done data collection as well. We've been using the DJI drones actually to collect data, mostly for breeders, so that they can get better varieties produced by giving them more data about the plants that they've been doing crossbreeding on. And that's great, and what I've seen so far in the commercial side of robotics in agriculture has been this huge groundswell of drones. People love drones and collecting data, and that's been a really popular theme recently in the commercial side of agriculture. But the challenge there is that the farmer doesn't really know what to do with the data. And so there's this gap still between our ability to collect tons of data and really interesting things about the field and the farmer's ability to take action. And so what I would argue is that the ability to collect data is great, but that data without action really isn't useful. And that's where robotics comes in. And maybe an analogy I'd make is data without action to me is a bit like having food without nutrition. So if you had your vegetables, but there's no nutritional value to it, you can consume all you want and feel full with it, but you really aren't getting any benefits. You're not doing anything with it. So we need to start taking actions. We need to start to use that data in meaningful ways. So what I put up here is just some examples, I think, of some interesting robots that are out there and work that's been done. And it's by no means comprehensive, but I just want to give people kind of a feeling of the types of things out there. People are using drones, starting to spray chemicals on the drones, doing targeted sprays. It's obviously limited by what you can carry. Some work in very constrained environments, so kind of tailoring the environment to the purpose of the robot. And there's been cool work there in nurseries and harvesting strawberries, things like that. What I think is even more exciting as we shift to the right side is devices and robots that are working outdoor in the environment, kind of in the native environment that the farmers are used to and that are working, so they don't have to make any changes to their environment. There's some really good research being done in Australia and in Europe on these types of systems, and you're starting to see more and more of these autonomous vehicles that are out there delivering operations in the farm. And some really cool harvesting ones. We haven't really focused in harvesting. Again, goes back to thinking about a startup company in robotics. Harvesting is one of the biggest, most difficult, challenging things you can do in agriculture. So we're not trying to start there. We'll build up to that over time, but there are some companies that are working in that area. If you haven't seen this, it's a great YouTube video on apple picking. It's a spin-off out of Stanford Research Institute called Abundant Robotics. Has a little arm that goes up to apples and just sucks them off the tree into this tube. It's really kind of fun, so worth checking out. So what I want to talk about is some of the work that we've been doing in robotics in agriculture. And the first area that we started with is an area called lettuce thinning. It's kind of an interesting situation in lettuce because the plants don't germinate very well. They have to overplant. So where they might want to plant, say, every 25 centimeters for it to grow well, they actually have to plant every 4 or 5 centimeters in order to get the plants to germinate well enough. And what that leads to is this overplanting, and they have to go then and manually thin out the plants. So that's why it's called lettuce thinning. They go with a hoe crew, usually 40 to 80 people that go through and walk through the field with a hoe and knock the plants out in order to kill them. And that works. It's been done for years. But it's really challenging for the growers because mostly of labor shortages. So there's real issues, like I kind of mentioned, of aging labor population. 45 years is a typical age for these laborers in the field. And especially in the US with stricter immigration laws, it's really hard to get labor, and it's hard to get consistent labor. So we've built this system. We've actually built 6 of these machines that operate in the field every day. We've done thousands and thousands of acres commercially. What you're seeing here is a system that has 18 modules. It does 18 rows of lettuce at once. Each of these modules has a camera and processing in it, so it's able to identify the plants, choose which plants to keep and which ones to kill, and spray them. We spray a fertilizer on the plants, which at this stage kills the young plants. So it's a great way to be able to go very quickly through the field and eliminate the plants that are not wanted. The dark patches you see are where the fertilizer's been sprayed. The little white gaps between them are the plants that have been left over. This machine runs, like I said, every day in real time. It runs somewhere around the order of 5 or 6 kilometers per hour. This machine will see about 1 million plants an hour, so it's a high throughput, high volume system. And we have run these across, we operate in about 10% of the lettuce grown in the US. So if you have a salad in the US, there's a chance that you've had salad that's been prepared with our machine. This is what it looks like after the machine's gone by. The dark spot again is where we sprayed. One of the things that's really critical is having to spray very accurately at high speeds. So we're able to spray within about 5 millimeters at very high speeds so that we can get between these plants that maybe only are a couple centimeters apart. And we do this reliably day in, day out, and that's one of the critical pieces. And then this is what it looks like a couple days after the fertilizers has kicked in and killed the plants that we sprayed and left and actually fertilized the plant that's left over, and that grows up to be harvested. That's kind of led us down a path, which is, again, this notion of moving from this broad acre coverage to what we call plant-by-plant care. So taking what I showed you earlier is this big boom that might be 20, 30 meters wide and spraying everything the same, to trying to transform that into something where we use computer vision and robotics to be able to spray each plant individually and treat each plant individually by collecting information about it and knowing what to do. The other thing that's important to mention, this broadcast spraying has led to real challenges with herbicide-resistant weeds. Kind of like the same way we've had problems with bacteria that's become resistant to antibiotics. The same thing. Overuse and misuse has led to the evolution of weeds that are now resistant to herbicides. And so 20 years ago, this was a bit of a problem. 10 years ago, it got much, much worse. Today, it is a challenge that every farmer faces, and they're having to just dig up their fields because the weeds have taken over. So you're seeing more and more prevalence of this. And the challenge is that they only have about 3 chemicals that they're allowed to use that work with the plants that they've got. So it's really constrained. It takes around 10 years to develop new chemicals and hundreds of millions of dollars. So basically the chemical companies are losing the war in the herbicide, in developing herbicides for weed control. Farmers also are seeing it every day. Like I said, they're having to sometimes give up on fields. The farmers actually will tell us, you can spray some of these herbicide-resistant weeds, and all it does is make them mad. The weeds get bigger and taller, and they grow. And some of the worst weeds, there's a weed called Palmer amaranth, or pigweed. It can have 1 million seeds that come out of a single plant. So they form this crazy, they call them seed banks, with seeds that come out of the plants. So again, our goal is to change the way we think about agriculture by providing plant-by-plant care, using robotics, using computer vision, and delivering just what's necessary to the plants. In this case, for weeding, it's delivering the herbicide just to the weeds. So we are going to focus on just delivering only to the weeds, not to the ground, not to the crop itself. We call this see and spray, so seeing the plants and spraying the plants individually. There's a lot of advantages there that we're seeing, and we're just in the stages of testing. I'll show you an example of it. First is that we can use any herbicide, right? So because we're not spraying the crop also, we're not limited to this very small set of herbicides. We can use any herbicide that's available and just spray it on the weed. We won't get it on the crop. We don't have to worry about damaging the crop or contaminating it with the herbicide. We're not spraying it across the ground. that also means that we can really target those weeds and spray what will kill the weeds. So we can target these weeds that have been problems for years for the farmers. And lastly, one thing I love is we're able to spray much less herbicide. We're only spraying where the weeds are, so in typical farms, that's only 10% of the coverage. So we can reduce herbicide usage by 90% or more. So how do we do it? Again, it's computer vision based. We take pictures of the plants just using a regular color camera and process that image. We're using deep learning, which many people, certainly people from robotics, are well aware of. It's all been hyped up very, very much lately. But if you haven't heard of it, it's a really powerful tool. And we're using it because it works, plain and simple. We're able to detect the plants. What you can see here, the green box is a lettuce plant in this case that's been detected by the system, and the red boxes are the weeds that have been all highlighted and identified by the system. This is an actual image, actual processing, the system running, and we're able to get accuracy rates in the 95, 98 percentiles for recognizing these plants and detecting the difference between them. And that's critical. We have to do really high recognition rates in real time because you can imagine if we had only like a 90% recognition rate, we'd go through the field and kill a bunch of the weeds. Sure, we'd leave a few, but then you got to go and turn to the farmer and say, yeah, I killed all your weeds, but I killed also 1 out of every 10 plant that you were trying to grow. They're not going to be very happy with that. So it's really critical to have a high accuracy, high speed system when you're getting out into the field with this. So this is a picture of our machine. This is the newest version, kind of beyond the lettuce thinning machine I'd shown you, that's targeted towards weeding. This one will do 8 rows at once, so each row is spaced by a little over a meter. So it's about an 8 meter machine, wide machine. It's pulled by a tractor, but all the decisions on board are done on board, by the computing hardware that's there. This is also a good example of engineers not even very good farmers. This field is supposed to be a cotton field, but it's just covered with weeds. So we tried to build our own cotton field and ended up with a bunch of weeds, which is great because we're trying to kill the weeds anyway, so it was great practice. But we definitely need to keep our day jobs as roboticists, not farmers. Here's a video of the machine in action. This is a slow version, so about ½ mile an hour. The cotton's planted right down the middle, and what you can see is the sprays that are being individually targeted towards hitting just the weeds. And we do this by having a camera that's identifying the weeds, like I showed you in the picture, and then a bank of sprayers that are individually spraying in the targeted locations. Almost like an inkjet printer, or if you're my generation, a dot matrix printer. It's spraying just where we need to, synchronized in time so that it sprays just the weeds. This is in lettuce going about 2 miles an hour. And so you can see it's almost hard to keep up with it just visually, but it's going through and spraying exactly just where the weeds are. It can spray between the plants. So it's able to kill all the weeds. And this is 2 miles an hour. The production machine has to go about 4 miles an hour for this year and 6 miles an hour for the next year. Because most of the farming operation is at that speed, somewhere around 6, 8, 12 miles an hour. And then this is one example of what this looks like. It's a little bit hard to tell what's going on here, but there's a cotton plant right in the middle that we needed to protect and save, and the weeds all surrounding it. And so this is a machine that was kind of running from your right to your left, going across the field, identified the cotton plant, identified the weed, and was able to protect the cotton plant by spraying around it and just targeting the weed. So the dark spot there is where the actual sprays hit and landed. So let me just kind of tie this all together and start to wrap up and let you guys go eat. So this is kind of where we see agriculture going. The idea is that we're trying to transform agriculture again from this very broad-based, one-size-fits-all application into something that uses computer vision, uses robotics technology to treat plants individually. I think there's some really interesting opportunities within agriculture. We're not working on it directly right now, but there's a lot of work on autonomous operations. So being able to have this tractor drive itself The big companies like John Deere are doing this, but a lot of the researchers are also working on that. And I think with driverless cars, it's very natural that we start to see that. We're working obviously in this kind of see and spray technology, so the idea of taking images of the plants, understanding what each plant needs and what each plant looks like, and then delivering targeted sprays in this case for each plant independently. We can do that not only with herbicide, but with fertilizers, with fungicides, insecticides. So a lot of the operations already in farming are using these sprays. So it's pretty natural to target spraying applications. And actually I should mention that because I get that question a lot. We've chosen not to do mechanical methods. People ask me why not use a till or some kind of mechanical tool. And the main challenge is speed. It's really hard to do things at high speed with something mechanical. And we've looked at mechanical methods, we've looked at boiling oils and acids and fire and Tesla coils to electrocute the plants and lasers. And all of them require you to have an extended period of time where you're in contact with the ground or in contact with the plant. So spraying turns out to be just a great way to deliver what you need to do and then move on. So you can do it extremely quickly. So back to the story, not only can you do then this individual treatment, but one of the things I really love about the potential of this ability to get in the farm, and again, it kind of goes back to this digital age where we're collecting data on this, is you can start to run these micro experiments where you optimize your system by running little experiments throughout the field. So you can imagine there's a ton of variation already in the plants in the field, so you get some variety in your data there. But you can also change your parameters as you go. And so you can run different levels of application in different areas and then come back either with a machine, maybe next time you come through to weed the next pass, or use a drone to collect data and tie that all together to optimize your system. So there's this continual process of kind of measuring and verifying things and learning from that and improving the system. And we've built that already into our system, the ability to learn on the fly and adapt on the fly and self-calibrate. But we're expanding that out across multiple operations in the farming process. So you can do this, in fact, we already give feedback to the farmers about how their planting was because we're measuring the planting, but you can do that throughout the process all the way through to harvesting. And it's, we kind of phrase it when we're talking to people this way, it's kind of extending in a very natural way the robotics methodology of sense, decide, act, where you're taking action and bringing in this verification step and learning from that. And we think that's a really critical part of this new agriculture where you've got this data, you're collecting data, you're in the field, you're taking measurements. Let's learn from that and adapt over time. All right, with that, I think it's time to break for lunch.